Okay, so where we are, so far we've talked about how to define a classifier using a function f parameterized by weights w. And this function f is going to take data x as input and output a score of a vector of scores for each of the classes that you want to classify. And so from here we can also define a loss function. So for example, the SVM loss function that we've talked about, which basically quantifies how happy or unhappy we are with the scores that we've produced, right? And then we can use that to define a total loss term. So L here, which is a combination of this data term combined with a regularization term that expresses how simple our model is. And we have a preference for simpler models for better generalization. And so now we want to find the parameters W that correspond to our lowest loss, right? We want to minimize the loss function. And so to do that, we want to find the gradient of L with respect to W. So last lecture, we talked about how we can do this using optimization, where we want to iteratively take steps in the direction of steepest descent, which is the negative of the gradient, in order to walk down this loss landscape and get to the point of lowest loss, right? And we saw how this gradient descent can basically take this trajectory looking like this image on the right, getting to the bottom of your loss landscape. Okay, and so we also talked about different ways for computing the gradient, right? We can compute this numerically using finite difference approximation, which is slow and approximate, but at the same time, it's really easy to write out. You know, you can always get the gradient this way. We also talked about how to use the analytic gradient, right? And computing this it's fast and exact once you've gotten the expression for the analytic gradient. But at the same time, you have to do all the math and the calculus to derive this. So it's also easy to make mistakes, right? So in practice, what we want to do is we want to derive the analytic gradient and use this. But at the same time, check our implementation using the numerical gradient to make sure that we've gotten all of our math right. So today we're going to talk about how to compute the analytic gradient for arbitrarily complex functions using a framework that I'm going to call computational graphs. And so basically what a computational graph is that we can use this kind of graph in order to represent any function where the nodes of the graph are steps of computation that we go through. So for example, in this example of a linear classifier that we've talked about, the inputs here are x and w, right? And then this multiplication node represents the matrix multiplier, the multiplication of the parameters w with our data x that we have, outputting our vector of scores. And then we have another computational node, which represents our hinge loss, right, computing our data loss term, li. And we also have this regularization term at the bottom, right? So this node which computes our regularization term. And then our total loss here at the end L is the sum of the regularization term and the data term. And the advantage is that once we can express a function using a computational graph, then we can use a technique that we call backpropagation, which is going to recursively use the chain rule in order to compute the gradient with respect to every variable in the computational graph. And so we're going to see how this is done. And this becomes very useful when we start working with really complex functions. So for example, convolutional neural networks that we're going to talk about later in this class. We have here the input, right, image at the top. We have our loss at the bottom. And the input has to go through many layers of transformations in order to get all the way down to the loss function. And this can get even crazier with things like like a neural Turing machine, which is another kind of deep learning model. And in this case, you can see that the computational graph for this is really insane. And especially, we end up unrolling this over time. It's basically completely impractical if you want to compute the gradients for any of these intermediate variables. OK, so how does backpropagation work? So we're going to start off with a simple example where, again, our goal is that we have a function. So in this case, f of x, y, z equals x plus y times z. And we want to find the gradients of the output of the function with respect to any of the variables. So the first step always is we want to take our function f, and we want to represent it using a computational graph. Right, so here our computational graph is on the right. And you can see that we have our first, we have the plus node, so x plus y, and then we have this multiplication node, right, for the second computation that we're doing. And then now we're going to do a forward pass through this network. So given the values of the variables that we have, so here x equals -2, y equals 5, and z equals -4, I'm going to fill these all in our computational graph. And then here we can compute an intermediate value. So x plus y gives 3. And then finally, we pass it through again through the last node, the multiplication, to get our final node of f equals -12. So here, we want to give every intermediate variable a name. Right? So here I've called this intermediate variable after the plus node q. And we have q equals x plus y. And then f equals q times z using this intermediate node. And I've also written out here the gradients of q with respect to x and y, which are just 1 because of the addition. And then the gradients of f with respect to q and z, which is z and q respectively because of the multiplication rule. And so what we want to find is we want to find the gradients of f with respect to x, y, and z. So what backprop is, it's a recursive application of the chain rule. So we're going to start at the very end of the computational graph, and then we're going to work our way backwards and compute all of the gradients along the way. So here, if we start at the very end, right, we want to compute the gradient of the output with respect to the last variable, which is just f. And so this gradient is just 1. It's trivial. So now moving backwards, we want the gradient with respect to z, right? And we know that df over dz is equal to q. So the value of q is just 3. And so we have here df over dz equals 3. And so next, if we want to do df over dq, what is the value of that? What is df over dq? So we have here df over dq is equal to z, right? And the value of z is -4. So here we have df over dq is equal to -4. OK, so now continuing to move backwards through the graph, we want to find df over dy. Right? But here, in this case, the gradient with respect to y is not connected directly to f. Right? It's connected through an intermediate node of z. And so the way we're going to do this is we can leverage the chain rule, which says that df over dy can be written as df over dq times dq over dy. And so the intuition of this is that in order to get to find the effect of y on f, this is actually equivalent to if we take the effect of q times q on f, which we already know, right? df over dq is equal to -4, and we compound it with the effect of y on q, dq over dy. So what's dq over dy equal to in this case? 1. Right, exactly. So dq over dy is equal to 1, which means if we change y by a little bit, q is going to change by approximately the same amount, right? This is the effect. And so what this is doing is this is saying, well, if I change y by a little bit, the effect of dq, effect of y on q is going to be 1, and then the effect of q on f is going to be approximately a factor of -4, right? So then we multiply these together, and we get that the effect of y on f is going to be -4. OK, so now if we want to do the same thing for the gradient with respect to x, right, we can follow the same procedure. And so what is this going to be? I heard the same. Yeah, exactly. So in this case, we want to, again, apply the chain rule, right? We know the effect of q on f gradient is -4. And here again, since we have also the same addition node, dq over dx is equal to 1. Again, we have -4 times 1, right? And the gradient with respect to x is going to be -4. OK, so what we're doing in backprop is we basically have all of these nodes in our computational graph, but each node is only aware of its immediate surroundings, right? So we have, at each node, we have the local inputs that are connected to this node, the values that are flowing into the node, and then we also have the output that is directly outputted from this node, right? So here our local inputs are x and y, and the output is z. And at this node, we also know the local gradient, right? We can compute the gradient of z with respect to x and the gradient of z with respect to y. And these are usually really simple operations, right? Each node is going to be something like the addition or the multiplication that we had in that earlier example, which is something where we can just write down the gradient and we don't have to go through very complex calculus in order to find this. Yeah, so basically, if we go back, hold on, so if we go back here, we could exactly find all of these using just calculus. So we could say, we want df over dx, right? And we can probably expand out this expression and see that it's just going to be z. But we can do this in this case because it's simple. But we'll see examples later on where once this becomes a really complicated expression, you don't want to have to use calculus to derive, right, the gradient for a super complicated expression. And instead, if you use this formalism and you break it down into these computational nodes, then you can only ever work with gradients of very simple computations, right? At the level of additions, multiplications, exponentials, things as simple as you want them. And then you just use the chain rule to multiply all of these together and get the value of your gradient without having to ever derive the entire expression. Does that make sense? Okay, so we'll see an example of this later. And so, was there another question? Yeah. Negative. Okay, yeah. So the -4, these were the green values on top were all the values of the function as we passed it forward through the computational graph, right? So we set up here that x is equal to -2, y is equal to 5, and z equals -4. So we filled in all of these values, and then we just wanted to compute the value of this function, right? So we said this value of q is going to be x plus y. It's going to be -2 plus 5, and it's going to be 3. And we have z is equal to -4. So we fill that in here, and then we multiplied q and z together, -4 times 3, in order to get the final value of f, right? And then the red values underneath were as we were filling in the gradients as we were working backwards. Okay. Okay, so right, so we said that we have these nodes, and each node basically gets its local inputs coming in and the output that it sees directly passing on to the next node. And then we also have these local gradients that we computed, right? The gradient of the immediate output of the node with respect to the inputs coming in. And so what happens during backprop is we have these, we start from the back of the graph, right? And then we work our way from the end all the way back to the beginning. And when we reach each node, at each node, we have the upstream gradients coming back, right, with respect to the immediate output of the node. So by the time we reach this node in backprop, we've already computed the gradient of our final loss L with respect to z, right? And so now what we want to find next is we want to find the gradients with respect to just before the node, to the values of x and y. And so as we saw earlier, we do this using the chain rule, right? We have from the chain rule that the gradient of this loss function with respect to x is going to be the gradient with respect to z times compounded by this local gradient of z with respect to x, right? So in the chain rule, we always take this upstream gradient coming down and we multiply it by the local gradient in order to get the gradient with respect to the input. So the question is whether this only works because we're working with the current values of the function. And so it works, right, given the current values of the function that we plug in, but we can write an expression for this still in terms of the variables, right? So we'll see that gradient of L with respect to z is going to be some expression, and gradient of z with respect to x is going to be another expression, right? But we plug in these, we plug in the values of these numbers at the time in order to get the value of the gradient with respect to x. So what you could do is you could recursively plug in all of these expressions, right? Gradient with respect z with respect to x is going to be a simple expression, right? So in this case, if we have a multiplication node, gradient of z with respect to x is just going to be y, right? We know that. But the gradient of L with respect to z, this is probably a complex part of the graph in itself, right? So here's where we want to just, in this case, have this numerical, right? So as you said, basically this is going to be just a number coming down, right, a value, and then we just multiply it with the expression that we have for the local gradient. And I think this will be more clear when we go through a more complicated example in a few slides. Okay, so now the gradient of L with respect to y, we have exactly the same idea, where again we use the chain rule. We have gradient of L with respect to z times the gradient of z with respect to y, right? We use the chain rule, multiply these together, and get our gradient. And then once we have these, we'll pass these on to the node directly before, connected to this node. And so the main thing to take away from this is that at each node, we just want to have our local gradient that we compute. Just keep track of this. And then during backprop, as we're receiving numerical values of gradients coming from upstream, we just take what that is, multiply it by the local gradient, and then this is what we then send back to the connected nodes, the next nodes going backwards, without having to care about anything else besides these immediate surroundings. So now we're going to go through another example, this time a little bit more complex, so we can see more why backprop is so useful. So in this case, our function is f of w and x, which is equal to 1 over 1 plus e to the negative of w0 times x0 plus w1 x1 plus w2. Right, so again, the first step always is we want to write this out as a computational graph. So in this case, we can see that in this graph, right, first we multiply together the w and x terms that we have, w0 with x0, w1 with x1, and w2. Then we add all of these together, right? Then we scale it by -1. We take the exponential, we add 1, and then finally we do 1 over this whole term. And then here I've also filled in values of these. So let's say given values that we have for the w's and x's, right, we can make a forward pass and basically compute what the value is at every stage of the computation. And here I've also written down here at the bottom the values, the expressions for some derivatives that are going to be helpful later on. So same as we did before with the simple example. Okay, so now when we're going to do backprop through here, right? So again, we're going to start at the very end of the graph. And so here again, the gradient of the output with respect to the last variable is just 1. It's just trivial. And so now moving backwards one step, right? So what's the gradient with respect to the input just before 1 over x? Well, so in this case, we know that the upstream gradient that we have coming down, right, is this red 1. Right? This is the upstream gradient that we have flowing down. And then now we need to find the local gradient. Right? And the local gradient of this node is 1 over x. Right? So we have f of x equals 1 over x here in red. And the local gradient of this, df over dx, is equal to -1 over x squared. Right? So here we're going to take -1 over x squared and plug in the value of x that we had during this forward pass, 1.37. And so our final gradient with respect to this variable is going to be -1 over 1.37 squared times 1 equals -0.53. Right? So moving back to the next node, we're going to go through the exact same process. Right? So here, the gradient flowing from upstream is going to be -0.53. Right? And here, the local gradient, the node here is a +1. And so now looking at our reference of derivatives at the bottom, we have that for a constant plus x, the local gradient is just 1. right? So what's the gradient with respect to this variable using the chain rule? So it's going to be the upstream gradient of negative 0.53 times our local gradient of 1, which is equal to negative 0.53. So let's keep moving backwards one more step. So here we have the exponential, right? So what's the upstream gradient coming down? Right, so the upstream gradient is negative 0.53. What's the local gradient here? It's going to be the local gradient of e to the x, right? This is an exponential node. And so our chain rule is going to tell us that our gradient is going to be negative 0.53 times e to the power of x, which in this case is negative 1 from our forward pass. And this is going to give us our final gradient of negative 0.2. Okay, so now one more node here. The next node is that we reach is going to be a multiplication with negative 1. Right, so here, what's the upstream gradient coming down? Negative 0.2, right. And what's going to be the local gradient? You can look at the reference sheet. It's going to be, what was it? I think I heard it. It's going to be minus 1, exactly. Yeah, because our local gradient says it's going to be df over dx is a, right? And the value of a that we scaled x by is negative 1 here. So we have here that the gradient is negative 1 times negative 0.2, and so our gradient is 0.2. Okay, so now we've reached an addition node. And so in this case, we have these two branches both connected to it, right? So what's the upstream gradient here? It's going to be 0.2, right, just as everything else. Here now the gradient with respect to each of these branches, it's an addition, right? And we saw from before in our simple example that when we have an addition node, the gradient with respect to each of the inputs to the addition is just going to be 1. Right, so here our local gradient for our looking at our top stream is going to be 1 times the upstream gradient of 0.2, which is going to give a total gradient of 0.2. Right, and then for our bottom branch, we do the same thing. Right, our upstream gradient is 0.2, our local gradient is 1 again, and the total gradient is 0.2. So is everything clear about this? Okay. So we have a few more gradients to fill out. So moving back, now we've reached W0 and X0. And so here we have a multiplication node, right? So we saw the multiplication node from before. The gradient with respect to one of the inputs just is the value of the other input. And so in this case, what's the gradient with respect to W0? I'm hearing minus 0.2. Exactly. Yeah, so with respect to W0, we have our upstream gradient 0.2, right, times this is the bottom one, times our value of x, which is negative 1. We get negative 0.2. And we can do the same thing for gradient with respect to x0. It's going to be 0.2 times the value of W0, which is 2, and we get 0.4. Okay, so here we've filled out most of these gradients. And so there was a question earlier about why this is simpler than just deriving the analytic gradient, the expression with respect to any of these variables, right? And so you can see here, all we ever dealt with was expressions for local gradients that we had to write out. So once we had these expressions for local gradients, all we did was plug in the values for each of these that we have and use a chain rule to numerically multiply this all the way backwards and get the gradients with respect to all of the variables.
이번 시간에는 뉴럴 네트워크, 특히 백프로포게이션에 대해서 알아보도록 하겠습니다. 지금까지 우리는 웨이트 W와 인풋 X로부터 스코어 X를 계산하는 방법을 배웠고 SVM 로스 LI를 계산하는 방법을 배웠으며 데이터 로스에 레귤러라이제이션을 더해서 전체 로스를 구하는 방법을 배웠습니다. 특히 그라디언트 L이 로스를 옵티마이제이션하는 방법으로 제시되었습니다. 옵티마이제이션은 산의 비탈길을 따라서 걸어 내려가는 것에 비유될 수 있습니다. 오른쪽에는 바닐라 그레디언트 디센트에 대한 시뮬레이션이 제시되어 있습니다. 그레디언트 디센트에서 Numerical Gradient는 Slow, Approximate, Easy to Write의 특성을 갖고 있습니다. 반면에 Analytic Gradient는 Fast, Exact, Error Prone의 특성을 가집니다. 실제로는 Analytic Gradient 방법을 사용하지만 Numerical Gradient로 임플멘테이션을 체크하는 방법을 사용합니다. 우리는 컴퓨테이셔널 그래프를 통해서 어떤 펑션이든 표현할 수 있습니다. 각 노드는 컴퓨테이션 스텝을 의미합니다. 리니어 클래시파이어의 경우 인풋은 매트릭스 W와 벡터 X이고 이를 곱한 값은 스코어 S가 됩니다. 이것에 힌질 로스를 적용하여 li 값을 넣고 regularization r 값을 더하면 전체 로스 L 값을 구할 수 있습니다. 이 그림은 컨볼루셔널 네트워크에서 인풋 이미지가 웨이트가 주어진 여러 뉴럴 네트워크 레이어들을 거쳐서 로스 펑션에 다다르는 것을 나타내는 것입니다. 뉴럴 튜링 머신은 딥러닝의 또 다른 모델인데 인풋 이미지에서 로스 펑션까지 매우 복잡한 구조를 갖고 있습니다. 아키텍처가 복잡해질수록 웨이트와 같은 intermediate variable을 계산하는 문제는 점점 더 어려워집니다. 이러한 문제를 해결하기 위해서 backpropagation을 사용합니다. 간단한 예를 통해서 알아보도록 하겠습니다. 예제로서 f of x, y, z가 x plus y times c의 함수로서 주어져 있고 오른쪽에는 이의 컴퓨테이셔널 그래프가 그려져 있습니다. 여기서 아웃풋 f에 대해서 인풋 x, y, z에 대한 그레디언트를 각각 계산해 보도록 하겠습니다. 백프로퍼게이션을 하기 전에 먼저 forward propagation을 해서 intermediate node 값을 계산합니다. intermediate node q는 x 더하기 y이고 f는 qc가 됩니다. 이 식에서 x에 대한 q의 그레디언트는 1이고 y에 대한 q의 그레디언트는 1을 얻을 수 있습니다. 또한 q에 대한 f의 그레디언트는 z이며 z에 대한 f의 그레디언트는 q입니다. 이들을 통해서 x, y, z 각각에 대한 f의 그레디언트 값들을 구할 수 있습니다. 아웃풋에서 f에 대한 f 그레디언트는 트리비얼한 케이스로서 1이 됩니다. 인풋에서 z에 대한 f의 그레디언트는 이미 계산한 바와 같이 q가 됩니다. 주어진 예제에서 q값은 3입니다. q에 대한 f의 그레디언트는 c인데 주어진 예제에서 z값은 -4입니다. y에 대한 f의 그레디언트는 체인 룰을 통해서 계산할 수 있습니다. q에 대한 f의 그레디언트에 y에 대한 q의 그레디언트 값을 곱한 것입니다. 이러한 체인 룰은 두 단계를 훨씬 넘어선 여러 단계에서도 사용할 수 있습니다. x에 대한 f의 그레디언트도 체인 룰을 사용해서 값을 구할 수 있습니다. 이러한 체인 룰을 이용한 백프로퍼게이션을 통해서 input x, y, z 각각에 대한 gradient f의 값을 구할 수 있었습니다. 다음 예제를 통해서 local gradient의 개념을 정리해 보도록 하겠습니다. 인풋은 x와 y이고 함수는 f이며 아웃풋은 z입니다. 여기서 x에 대한 z의 gradient, y에 대한 z의 gradient는 local gradient라고 합니다. backpropagation에서는 upstream gradient가 거꾸로 되돌아오는 것을 볼 수 있습니다. 이 경우에는 z에 대한 final loss L의 gradient입니다. backpropagation에서 우리가 원하는 것은 x에 대한 loss L의 gradient입니다. 이는 체인 룰을 통해서 계산할 수 있습니다. 마찬가지로 y에 대한 로스 L의 그레디언트를 체인 룰을 사용해서 계산할 수 있습니다. 딥러닝에서 여러 레이어가 있을 경우 다음 단계 레이어로 백프로퍼게이션을 계속 진행할 수 있습니다. 이번에는 좀 더 복잡한 펑션에 대해서 백프로퍼게이션을 계산해 보도록 하겠습니다. 아래에는 이해를 돕기 위해서 4종류의 그라디언트식들이 제시되어 있습니다. 백프로퍼게이션은 아웃풋부터 인풋 방향으로 한 단계씩 진행하도록 합니다. 이 경우 x에 대한 f의 그라디언트는 마이너스 1 나누기 x 자승입니다. x값은 1.37이기 때문에 그라디언트 값은 마이너스 0.53이 됩니다. 다음 단계에서는 x에 대한 f의 그라디언트는 1입니다. 따라서 그레디언트는 마이너스 0.53이 됩니다. 다음 단계에서는 x에 대한 f의 그라디언트는 exponential x가 됩니다. 따라서 그라디언트는 마이너스 0.2입니다. 다음 단계에서는 x에 대한 f 그라디언트는 마이너스 1입니다. 따라서 그라디언트는 0.2가 됩니다. 이번에 플러스 노드는 두 개의 인풋을 갖고 있습니다. 각각의 인풋에서 로컬 그라디언트에 업스트림 그라디언트를 곱한 것은 0.2가 됩니다. 이번에는 곱하기 노드입니다. 로컬 그라디언트는 다른 쪽 인풋의 값을 가지게 됩니다. 따라서 x0는 0.4, w0는 마이너스 0.2의 그레디언트 값을 가지게 됩니다.